Welcome to the second talk of the morning session. We have with us Bingrong Huang from Shandong University, China. He will be talking about quantum variance for automorphic forms.
Thank you very much for the introduction. So I'd like to thank the organizers for inviting me to this nice meeting. So I'm very glad to speak here. So today I will talk about quantum variance for automorphic forms. So I view this as an application of error functions and the circle methods. This talk is based on the joint work with Stephen Lester. Okay. So my plan is this. So I will briefly introduce quantum chaos and the automorphic forms. Then we will discuss quantum variance for Hecke-Maass cos forms and Einstein theories. Then I will introduce Dihedral Maass forms and their quantum variance. And in the end, I will give you some proof ingredients, including error functions. Okay. So in Kam's talk yesterday, we already see arithmetic quantum chaos. So in the classical world, we let M to be a Riemann surface. Then you can consider it's a unitary bundle. Since this is a Riemann surface, we have Riemann metric. So we have the geodesic flow on this. And then we can condense it to get to go to the quantum world. So in this setting, we will consider this R2 space on M. So in particular, since we are Riemann metric, we have the corresponding Laplacian operator. Okay. So in quantum dynamics, we will consider the orthonormal basis consisting of eigenfunctions of the Laplacian. Okay, so right now we write it as a psi j here. So also this is dimension 2 case, so we will use a spectral parameter Tj instead of the eigenvalue lambda j. Okay. So Weyer's law tells that the number of Tj up to capital T is roughly a constant times T squared. Okay, so we have many eigenfunctions and eigenvalues. Okay. So yesterday we already see this random wave conjecture due to McBarry. So he suggested that for chaotic systems, those eigenfunctions should behave like random waves in the semi-classical limits. So here semi-classical limit means that these eigenvalues tend to infinity. And mathematically, we can write down this as a value distribution. It should be Gaussian. So we can consider, for example, this LP norm. Okay. So here, chaotic systems means that in the classical dynamics, this geodesic flow is ergodic and also this exponential divergence of orbits and maybe more. Okay. So yesterday we see a LP norm, but today we will mainly consider a family of metric elements. So we consider this a fluctuation of metric elements. So we take A to be an observable, it's just a smooth function on M, and we can condense it to get an operator. So this operator is actually a multiplication operator. So just map F to A times F. So this op A is an operator now. So we have this orthonormal basis. Then we can consider this metric elements. So this is the JJ's metric elements. So we view this op A as a infinity times infinity metric. So this is JJ's metric. This is diagonal metric. Okay, and this guy is actually defined by this integral on M. So this is just A times a psi j square absolute square. Okay, so this is the JJ's metric elements. So we care about the fluctuation of these metric elements as J vary. Okay, so the local Weyer law will tell us that the mean value of metric elements is asymptotic equal to a classical average. So we have this asymptotic formula. Okay, this NT is just Weyer law, right? Okay, and moreover, we actually have this a quantum ergodicity theory. So if we first assume this geodesic flow of M is ergodic, so we assume this, then we can get a quantum ergodicity. Okay, this is due to Schneiderman created a video and z-ish. Okay, so which says that the variance for these metric elements vanish. So we define this quantum variance by this guy. So this is 1 over total number of eigenfunctions we are considering. Okay, here we take this JJ's metric elements minus its mean and take absolute value and square it. And we think this, then they can show that this guy vanished. So from this, we actually know this mean result. Okay, this is a simple consequence of this quantum ergodicity theory. And moreover, a direct consequence of this variance estimate, we know that for density 1, these metric elements, we actually this metric elements actually has this asymptotic formula for density 1 psi j. Okay, so not only for the mean, but also for density 1 metric elements, we actually have this very nice asymptotic formula. This is what quantum ergodicity tells us. Okay. And also there is or even better conjecture here. So we have this so-called quantum fluctuation conjecture due to Rowe's physics. Okay, so if we normalize this mean of A to be 0, then and also have stronger assumption. So this geodesic flow is chaotic, and then generically, which means that for almost all chaotic systems, we hope this the following two hold. Okay, so the first thing is this variance. This is just defined the previous slide. Okay, so this variance is not just vanish, but actually has an asymptotic formula which has t to -1 here. So as t go to infinity, this guy will go to 0 for sure. Okay, and also in this asymptotic formula, we actually see this classical variance. So in our talk, it doesn't matter what it is. You just think this is a constant corresponding to the classical dynamics. Okay, so we hope this asymptotic formula to hold. Okay, and also moreover, we can also consider higher moments. So here, if we normalize these metric elements, so we have another factor here, then we expect this has a Gaussian distribution with mean 0 and the variance is equal to the classical variance. So this is a very nice conjecture. Okay. Okay. And but we have to say that it's generically true. So for example, you already see that for our arithmetic setting, this is not really true. Okay. Okay, is there any question? Okay, good. So now we go to automorphic forms. So I think most of you already know this very well, but here I just want to introduce the notations. Okay, so H is a upper plane. So this we have Laplacian, and geodesic is a symbol, and the gamma will be the modular group or this Hecke congruent subgroup. So here capital D is an integer. For example, this is 21. So in our talk, we think D is fixed. So we fixed capital D. Then this hyperbolic surface is just this quotient space, this H mod gamma or H mod gamma not D. So actually, if we are not consider Dihedral Maass forms, then we will only consider level 1 case, this H mod gamma. But if we are considering this Dihedral Maass forms, we have to have some level. So here we will take the second case. Okay, so in this talk, since D is fixed, so we will not distinguish these two. We will not be very careful about what X will be. Okay, since this Gauss curvature on X is negative, so this is a chaotic system. Okay, good. Then we have a Hecke-Maass forms. Okay, so if we have some level, we only consider new forms. So we have some non-trivial Niven-Tappers, but this is not very important. Okay, so whereas law here also is explicit maintained here, so it's t squared. Okay, we only need to know that this is t squared. Okay, and in this Hecke-Maass form case, we use uj, this family uj to be this orthonormal basis. Okay, good. So now instead of consider a one metric elements, we consider a family of metric elements. So here we consider a family of mass forms. Then this is a picture for its mass distribution. Okay. And we also have Einstein series. Okay. So here we give a definition for this. This is a sum, and for a real part is large enough. And then we have a Fourier expansion. From this, we know analytic continuation of Einstein series as a function of S here. Okay. So by Seibel spectral decomposition, we know that this L2 space is actually a constant and correspond space, and this generating by this Einstein series. So we have three parts. Okay. But constant function is very simple. So essentially, we have two space corresponds and continuous this continuous spectrum part. Okay. So we already see this continuous godicity yesterday. Yeah, right. So we have these metric elements. Then Lunig and Sarnak conjecture that we have a unique godicity. So from this quantum godicity, we know that for density 1 metric elements, we have this asymptotic formula. But Lunig and Sarnak conjecture that we have unique. Okay, so there's no other limiting measure here. So this is for OJ, we actually have this asymptotic formula. So we also can consider similar things for Einstein theory. So this was this analog QE is was proved by Luo and Sarnak. So they can prove this asymptotic formula for OT as t go to infinity. So and this is the right hand side is not exactly the same as the corresponding case. So we have extra logarithmic factor here. So this guy, if you split this this 6 to be 3 times 2, then this is actually a log t squared. Okay, so this is another factor here. And for a dihedral mass form, I will define the dihedral mass form later. So QE for dihedral mass form was proved by Peter Sarnak and Jianya Liu and Yang Boye. Okay. And then we have the famous results of Linus Strauss and Sand. They prove this QE for Hecke-Maass class forms. Okay. And for holomorphic forms, this was proved by Horowinski and Saurabh. This is for individual metric elements. But Sarnak also considered this quantum variance. So we take these metric elements, we average over this Tj here. So the first result in this setting is due to Luo and Sarnak, and later Zhao Peng and Sarnak Zhao. And also in the level aspect, Paul Nielsen also did some very nice work in this setting. Okay, so for class forms. So for example, I list one result here. This is maybe due to in Zhao's paper. Okay, so we define this a quantum variance for class forms by this limit. Okay, so here we have this. Hello. Okay, so we define this metric elements for phi and the metric elements for psi. The product of these two, then we average over Tj. This Tj means that from capital T to T. Okay, then we divide T here. So know that we have this normalization. Then we define this as a quantum variance, and the phi and the psi are choosing from a class form. Okay, these are orthonormal basis. Then they can show that this quantum variance is equal to this guy. So as t go to infinity, this guy will have certain asymptotic formula for this inside sum. Okay. So if phi and the psi are equal, then this is absolute square. Then we know that we hope there's some momentum. So this is the contribution for the momentum. So we have classical variance and some explicit oral product. This is some constant. Okay, and interestingly, we also have this central error value here. So if this phi is an even mass form, okay, so we have this central error value. This is because we are in a arithmetic setting, right? So generically, we don't expect these two factors appear. Okay? But in arithmetic setting, it's very close to the conjecture, but not exactly. Okay. For the covariance, we actually see that this covariance will vanish. Okay, so we get 0 here. And for in this arithmetic setting, we can compute this classical variance. This is just ratios of gamma functions. Okay, so to prove this, they use a Watson formula and Kuznetsov-Chase formula and the Poincare series to show this covariance vanish and also Hecke operators, etc. Okay, and they also prove a more general result, but I only state the result like this. And for Anson theory, we can prove analog results. So since this a continuous spectrum is parameterized by Anson theory, so we consider this we also call it metric elements, but it's not really, it's not infinity times infinity metric here. It's continuous. Okay, so we define mu j as this inner product. Since psi here is kind of a cost form, so this integral is well defined. Then we define this a quantum variance for Anson theory. So we take an average as this integral from t to 2t, and we should normalize it correctly, right? So here we have this 1 over log t here. Then we can show that if this phi and psi are taken from this orthonormal basis, then we get this quantum variance for Anson theory is equal to this guy. So here, if phi and psi are equal and even, then we have similar things. We have classical variance, but here we have for our central value, we actually have square here. And we have certain order product here, explicit, but complicated. So I didn't write down this here. And also for a covariance, we can also show that this is equal to 0. Okay, so this is our result for Anson theory. So in fact, to do this, we actually consider this integral before we take this limit. And for this, we can actually prove a quantitative error term here. We get asymptotic formula, we quantitative error term here. And also by Lunik and Song's idea, we can actually show that higher moments blow up. So no central limit theory. So this is not Gaussian distribution. Okay. So we can also know the results for all higher moments. This is for the low bound for moments of our functions. So for people, you know, okay. So this is our result for Anson theories. So I will first introduce the results, and then in the end, I will say a few words about the proof. So is there any questions for the statement? Okay, good. So now I will introduce Dihedral Maass forms and then give you the quantum variance for Dihedral Maass forms. Okay. So here we first defined this Heckle Grossencharacter. So we take a real quadratic field. So this D is a fundamental discriminant. So this is square free and mod 1 congruent to 1 mod 4. Okay. So we have this real quadratic field. And for simplicity, we only consider this a narrow class number equal to 1, and D is actually a product of two distinct prime congruent to 3 mod 4. For example, in our talk, we actually consider this D is 21. Okay, so this is 3 times 7. Okay, so this the foreign notation are standard. Maybe it's not important to introduce them. Okay. So then we have this a Heckle Grossencharacter. We denote it by K for K be an integer. So this is defined by this guy. And to choose this, since we assume a narrow class number is equal to 1, so this is well defined. And since we have this log factor here, so this is not this. The right hand side is not dependent on the generator of this idea. Okay. So this is well defined. So there's kind of some character here. and use this character, we can actually construct a theta-like theory. So we denote it by phi k corresponding to this K. So this is a complicated sum, but we don't know. We don't need to know the exact expression for this. So we need to see that there's a Heckle Grossencharacter here and the KPSI function, etc. Then this theory is actually belong to this a new form. It is actually to normalize the new form with 0 and this level D, and with some Nibben-Taber's character here, corresponding to this real quadratic field. Okay, so we only need to know this, and the spectral parameter for this Dihedral Maass form is pi times k over log epsilon d. Okay, good. So we normalize it. Then I want to explain a little bit about this wire law. So for Dihedral Maass forms, the wire law is really simple, right? Since this spectral parameter is explicit dependent on k, right? So if we counting tk up to capital T, we can count this. So we have very nice asymptotic formula. But here we see that as t go to infinity, this is linear, right? This is t, non-constant times t. But for all Hecke-Maass cos forms, we already see that the wire law tells that the number of all Hecke-Maass cos forms up to with spectral parameter up to capital T is roughly t squared. So this Dihedral Maass form is really distinguished subsequence of all cos forms. Okay, so we are considering we will consider average over all Dihedral Maass forms. So this is really a subsequence of this. So here we use the same notation for these metric elements. So this is the inner product of a test function or an observable and this absolute square. Okay. So for a quantum variance for Dihedral Maass forms, we defined by this. So we average over k. We take smooth average, but it's not really very important. Okay, and here we have two metric elements. So we want to understand the quantum variance for this. Okay, so we will take capital K to go to infinity. Okay, and in this setting, it's actually more complicated. So we also defined this harmonic weighted quantum variance or covariance. Okay, so here we weighted by R value at 1. So here we normalize this R function to have central point 1/2. Okay, so this is really only age. Okay, so we have this R value at 1, this factor here. Then we call it a harmonic weighted quantum variance. So we define this too. Actually, for cos form case and Einstein theory case, we also have this harmonic weighted quantum variance. But to remove the harmonic weights in that settings is kind of okay. So we will not lose too much. But for this Dihedral Maass forms, we will have some important difference. Okay. So in a joint work with Stephen Lester, we can compute this quantum variance for Dihedral Maass forms here. So if we consider a variance, so we say that phi1 equal to phi2 equal to phi, then phi is an even Hecke-Maass forms. Then we can compute, we can get this asymptotic formula. This is kind of complicated. So we have some factor depend on this weight function, and we have some factor depend on the underlying real quadratic field. So this is P1, P2 is P1 times P2 is equal to D. So this is 2 prime congruent to 3 mod 4. Okay. So we also have this central error values here. So this will be a G02 error function times a twisted G02 error functions here. So we have 2 central error values, and we also can get this classical variance. Okay. to get this asymptotic formula unconditionally for this harmonic weighted sum. But to remove these harmonic weights, we lose something. So we can only do this by assuming this generalized Ramanujan conjecture. Okay, so with this conjecture, we can show that we can remove this harmonic weight to get asymptotic formula. Just replace this AH by A. This A is actually some constant with another explicit constant, but really complicated one. Okay, so we can prove this asymptotic formula. In fact, we can have more precise results for this little one. Okay, and as an application of this quantum variance results, so it's not very important one, but we have some application. So if this in this main term, if this guy is not vanished, so for this guy, maybe you can show that this is not vanished. And for this central value, there are conjectures that at least for almost all psi, this is not vanished. Okay, then we can know this omega result for these metric elements. But from the quantum variance for Hecke-Maass forms, so for the whole class forms family, then we can also get this omega results, but only for Hecke-Maass class forms. But since this Dihedral Maass form is really a subsequence of that, so from that we cannot get the omega result for these Dihedral Maass forms. Okay, and also if you assume a generalized Riemann hypothesis, then we actually see that this metric elements is bounded by k to a minus 1/2 plus epsilon. So we only have a gap k to a epsilon here. Okay. Yeah, this is a main result for quantum variance. Okay. So we also consider this covariance for Dihedral Maass forms. Okay. So for covariance, since in this setting we cannot do this unconditionally, but we can use moments of error functions to do this by assuming this generalized Riemann hypothesis. This is an even stronger assumption. So with this conjecture, we can consider covariance, which means that psi1 is not equal to psi2. Okay, in this setting, we can show that this covariance actually vanish. Okay, as k go to infinity, this go to 0. So why we need to do this? Because to understand this covariance, this has a consequence. So which says that if we view this Q, psi1, psi2, two variables, we view this as a quadratic form, and then we actually, with this result, we actually know that this quadratic form is diagonalized by this orthonormal basis of Hecke-Maass hospital new forms in this space. Okay, in this new form space. We didn't consider other space. Actually, our method can do this, but we didn't do it. Okay, and also use Zev-Lunick and Song's idea for these moments of error functions. We actually can show that higher moments blow up, and also these higher moments for these metric elements also blow up. Okay. Okay, so maybe I go too fast. So now I will try to give you some ideas of proof. Okay. So in all these quantum variance results, we actually use a Watson's formula or Rankin-Selberg's method to relate these metric elements to central values. Okay, so here in the level 1 case, we use phi and uj as Hecke-Maass forms, and for the Dihedral Maass forms, we use phi k as the Dihedral Maass forms. So we have some certain level here, but also as the observable for this test function is psi. Even in a level D case, we actually need to consider this trivial Nibben-Tapers case, since if we are considering this its metric elements, right? So we have phi k square, absolute square, then this will become a trivial Nepentavers. So we, for this precise, we actually consider a trivial Nepentavers case. Okay. So by Rankin-Selberg method, we can relate this natural elements for Einstein theory to these GO2 L functions. So we have GO2 L functions at 1/2 plus 2it, and also another GO2 L functions at 1/2. Okay. So we also have L functions on the one line. Okay. Here, this is the complete function of Riemann zeta function. Okay. Good. So this use this formula, we can try to prove a result for Einstein theory. Okay. But for a mass form, class form case, we actually need to use Watson-Ichino's formula. So here for level 1 case, this is due to Watson. So we have this result. So this absolute square will equal to this central L value here, and also L value at 1 here. So we have this symmetric square times GO2 form, and here we have GO2 here. And for this dihedral forms, so this K, although J and K can both equal to 1, but we just use this notation to distinguish. So here is for level 1 form. So here mu K means that for dihedral form. Okay. So in this case, for dihedral mass forms, so we actually know that this symmetric square of phi K actually can decompose as a Riemann zeta function and this phi 2k. Okay, so here we see that maybe Riemann zeta function or Dirichlet L function, I didn't remember. Okay, so here this degree 6 L function can be decomposed as a degree 2 L function and a degree 4 L function. Okay, so we have degree 2, and degree 4 L functions, the product of this. So now we already can see central L values appear in the asymptotic formula for quantum variance now. So for Hecke-Maass forms, so we already see that this we have one central L value here, right? And for Einstein theory, we actually have square here. But for this dihedral mass forms, we actually have this base change L function. So this is GO2 times twisted GO2. So for those things, we will appear in this asymptotic formula for quantum variance, since we are for Einstein theory average over T. So this is not dependent on T. And for Hecke-Maass class forms, we average over J, and here we average over K. So we already see this central L value will be there. We will not change. Okay, after we take this average. Okay, so now we already see that to estimate this quantum variance, we actually only need to consider these moments of L functions, right? So for following 2 slides, I will discuss quantum variance for Einstein theories. So we related to this integral moments of L functions. So here, by Rankin-Selberg's method, this quantum variance for Einstein theory actually is related to this weighted second moment of GO2 L functions here. So phi and psi can be different, and also this we have certain weight here if we didn't consider this harmonic weighted sum, harmonic weighted quantum variance. So if we consider this original one, then we have this L value on this one line. Okay, so this W is a nice weight function. Okay, so in order to remove this this weight, so this harmonic weight is just to cancel out this. So if we take a Riemann zeta with power 4, then we just cancel out this. Then this is quite standard. This a second moment of it kind of related to second moment of GO2 functions due to good, right? And also here in order to remove this, we will replace this zeta value at one line by a short Dirichlet polynomial here. So we use since it's 1 over zeta value, so we will use prime number theory. So for T large, then we can take a small x. So we have this Dihedral polynomial here with the coefficient is just mu convolved mu. Okay, so we have certain weight. Then this Ayrton is just similar to what we can have for the prime number theory. So we use this zero-free reason to get this. Okay, so this is kind of standard. Okay, but the bad thing is that this Ayrton is not very good. So we didn't get a power saving of t here. So no matter how good we can do for this Dihedral polynomial, this Ayrton will not be too good for these moments of our functions. Okay, so we didn't try to do very hard for this Dihedral polynomial. So okay, so for this second moment, I think everybody here knows very well about this how to estimate this second moment of our functions. Or this is just two GO2 error functions, but we different sign here. So we use a approximate functional equation, and then integral over t first. Then we will see that we will have this shifted convergent sum. Okay, so we already see this shifted convergent sum in Ganguly's talk, right? So, but here we have slightly a more general setting. So here, maybe I don't want to introduce this Ross conditions, but I should say that this theory, I use the theory of Heckle. Okay, so he can prove this quite general setting. So with some conditions on this weight function, this f, then for this shifted convergent sum is two GO2 free coefficients here, but this shift is kind of more complicated. So this k and l is can be large, but not too large. Okay, then for this uniformly in H, Heckle can prove this non-trivial upper bound if this p and the kl are not too large. Okay, for fixed phi and psi. Okay, so you can prove this. So roughly speaking, you can see that the trivial bound here is roughly x over k or y over l, the minimum of these two. So here we get something like if x equal to y, k equal to l, this you can see that there are some power saving here. So this is already good enough because here in this Ayrton we didn't get power saving. So if for this part we can get power saving, then it's enough for this quantum variance. Okay, yeah. For this shifted convergent sum, I think Heckle used a utilitarian circle method and Voronoi summation formulas to prove this. And here I think the constant depend on epsilon and phi and psi, and also maybe he can deal with quite general phi and psi, not need this level 1 or trivial Nibben-Tappers, etc. Okay, so for quite general phi and psi, he can do this. Okay, this is what circle methods come in. Okay, good. Is there any question? No. Okay, now I want to say something about this Dihedral Maass forms. So to prove this quantum variance for Dihedral Maass forms, we actually reduce them to this moments of GO2 times GO2 functions. But this is an unusual moment, right? Since our family is this Dihedral Maass forms. So for this, I think there is a result for the level aspect due to Templier. In his thesis, he actually considered similar things for Dihedral Maass forms. But here we consider this a kind of spectral aspect for Dihedral Maass forms. So maybe I won't say too much about these conditions here, but just think that psi is fixed. Okay, then we have this family of Dihedral Maass forms here, and we have certain smooth weight. Then we can compute this first moment here. So we get asymptotic formula here. So with as you expect, this is we have momentum is linear in K, and we have a power saving. So here theta is corresponding to the Ramanujan-Selberg conjecture. So if conjecturally this is 0, so we get square root cancellation. If this W is nice enough, then we get square root cancellation here. So we get very nice asymptotic formula here. And yeah, and for this constant, this CD psi, this is actually depend on this underlying real quadratic field. Okay, so we have we are not only we have this capital D, but we have this P1 and P2. So this D is equal to P1 and P1 times P2. So we have this really have information about this real quadratic field. More importantly, we have this error value at 1. So as you know, by this, I think Dihedral can show that this is related to the class number, right? So this is but in our work for simplicity, we actually only consider the case with class number equal to 1. So this is simple. So we don't really try to work out the dependence on this real quadratic field, but we can see some dependence. Okay, yeah, good. This is what we can do for the first moment. But and use this result, we can show this asymptotic formula for this harmonic weighted quantum variance for dihedral mass forms. But to remove this weight, to remove this harmonic weight, we have some error value at 1 over this error value at 1. So to remove this, we actually need to consider this twisted first moment. So we have certain Fourier coefficient here. So we have twisted by GO2 Fourier coefficient here. Then to prove this asymptotic formula, in order to consider this, to estimate this contribution from off-diagonal term. So to show that off-diagonal term will not contribute to the main term, we assume a generalized Ramanujan conjecture. Otherwise, we can just have a very ugly main term there, but we don't really know the value of that. But if we assume a generalized Ramanujan conjecture, then we can have a clean asymptotic formula here. So similar main term and also this error term, but also we depend on this twist. Okay, so we have n to some power. Okay, so we will see that why we need Ramanujan conjecture later. Okay, so for a quantum variance for dihedral mass forms, use this Watson-Ichino formula. We actually need to compute this weighted first moment. So we can, like the quantum variance, like the Einstein theory case, we can replace this 1 over this error value by a short Dihedral polynomial. Then we can actually use this twisted first moment to estimate this weighted first moment. Okay, so to prove this, we also use Ramanujan conjecture. Okay, so this is our result for moments of error functions. Okay, so to prove this moments of error functions, so we will use this average over k, right? So for the average over k, we actually use Poisson summation formula to deal with that. And then this average tells that we actually should reduce to the sum to some of these ideas to a certain sector. So which means that we have some conditions on restrictions on these angles of these ideas. Okay, so with this restriction, we can actually reduce this moment to this non-split sum. So here, lambda phi is a GO2 Fourier coefficient, but instead of this shifted convolution sum, we actually we have this non-split sum. So which means that we have GO2 Fourier coefficient, and this is a an irreducible quadratic polynomial here, and then we have this average. So this but for shifted convolution sum, we actually kind of have this quadratic polynomial is kind of reducible. Okay, so we have this irreducible setting. But I didn't try to simplify this slide, so I'm sorry. So, but you can ignore those conditions. Okay, so here we just see that we have this a non-split sum. So we want to deal with this non-split sum. For this kind of sum, if we take b equal to 0 and a equal to 1, then this was studied previously. So I think for a divisor function, this was first dealt by Huli long time ago. And for divisor function, you have some special tools, right? And later on, Peter Sarnak have this idea that this Poincare theory approach for this shifted convolution sum can be used to this non-split sum here. Okay. Then for this holomorphic case, Bromer can use. I think you already see these techniques in Ganguri's talk. So for holomorphic Fourier coefficient, you can write it as a sum of Grossman sums. Then this quadratic polynomial will go to Grossman sum. So by that approach, Bromer can prove a nice asymptotic formula for this guy. But for a mass form case, this approach will not work. So Templier use a kind of complicated method to deal with. Actually, to be honest, I didn't understand his method very well. Okay, but then I think yeah, Templier and Zimmermann they use a method of Bromer and Happus for this shifted convolution sum. They use that to deal with this non-split sum. But in all previous works, they actually need this b equal to 0. I will explain why later. Okay, so if b is equal to 0, then things will become simpler. Okay, so for this non-split sum, we can prove this result. Okay, so the same setting, then this non-split sum we have an asymptotic formula with some explicit constant depend on psi a b c. Okay, and then we have square root cancellation up to Ramanujan conjecture. Then we have this certain power saving here. So the second result actually show you the difference between a b equal to 0 and a b is not equal to 0. Okay, so this is because we have this assumption for capital D. So we have this. This is not very important. The most important condition is that A divides B. So if B equal to 0, then for any A, we actually have this A divide B, right? So then in this setting, we can show this constant equal to 0. So we actually don't have maintain. So this can be done unconditionally. But if we don't have A divide B condition, we don't have this condition, then I don't know. We don't know how to show that this constant will vanish. Okay, so but the good thing is that we can use a multiplicative number theory. So we consider this. Actually, we view this if we have Ramanujan conjecture. We can view this as a nice multiplicative function. Then for this sum of multiplicative function over certain polynomial, we can actually have a related to sum of primes. So we can have some good upper bound for this. Then use that, we can show that this constant equal to 0. Okay, so here is an expression of this constant here. So here, since we have a irreducible quadratic polynomial, so we will have a mass forms of half integral weight. So this kappa is kind of I think it's 1/2 maybe. Yeah. So this we will have a Hecke-Maass forms of half integral weight. Okay. So this condition means that we need to remove this linear term in this quadratic polynomial. So we want to reduce this sum to this sum. Then we have this sum of these characters. So if b equal to 0, then we don't have this thing. So for this inner product, this psi j will be this fj will be simpler. then we can show that this inner product is equal to 0. Then this is the reason why we can prove item 2 unconditionally. But in general, we don't know how to deal with this inner product here. So we don't know how to show this equal to 0, this vanish unconditionally. Okay. Yeah, this is for a non-split sum. Okay. Is there any question? And maybe I only have one slide, so maybe let me finish this. Okay. So for covariance, we actually use another method. So for class form case, to prove this covariance vanish, actually Low and Sarnak use Poincare series as the test function, and then use Hecke operators and this Laplace operator to show that this quadratic form actually can be diagonalized. Then they can prove that this covariance vanish. Okay, but that approach is not seems not working for this Dihedral Maass form case, and also for this quantum covariance for Einstein theory, we actually just need to since we have a Rankin-Selberg method, so we can relate to moments of our functions directly. So we can estimate like a moment. So we can deal with the covariance similarly. But for Dihedral Maass forms, we actually don't know how to prove this covariance vanish unconditionally. But we can use a beautiful result of sound. So he found that assuming Riemann hypothesis, one can prove almost sharp upper bound for these moments of Riemann zeta functions, and more generally moments of L functions. So up to log epsilon, we can prove almost the best upper bound. Okay, so here we use the same idea to consider this products of these Rankin-Selberg L functions. So we have a certain power here, positive, and we have a distinct psi 1 and psi n. Then we can show that we have certain upper bound. Up to epsilon, this should be optimal. So for covariance, we actually need to have this n equal to 0. We have 2 psi 1 and psi 2, and L1, L2 we are equal to 1/2. Since we have metric elements, the absolute value square of these metric elements is equal to this central L value, right? So for metric elements, if we take absolute value, then it will relate it to this Rankin-Selberg L function to a power 1/2. So we have this L1 and L2 equal to 1/2 for quantum covariance. So with this, then we see that in the right-hand side, we actually have 1/2 minus 1. So this is negative. So we get some log k to some negative power. So this shows that as k go to 0, this will be little ok. Then this guy means that this covariance for the Dihedral Maass forms vanish. Okay. So this is all my talk. Thank you very much.
Thank you. So any questions from the audience?
Yeah, thank you for a nice talk. Has anybody tried to do this for H3, I mean SL2 over imaginary quadratic fields?
Actually, Qizhi and I and other people are trying to do this. Yeah,
Who,
we're still working on this. Yeah.
I can't hear, couldn't get you. Who did you say?
Qizhi, yeah. Zhiqi, yeah. Another speaker yesterday. Yeah.
But he gets similar quality results, or?
No. For three-dimensional case, we think we maybe not be able to prove asymptotic formula, but we can. It's possible to prove a almost sharp upper bound for
Ah.
quantum variance. Yeah,
I
but to
see.
prove a symptotic formula seems quite hard.
Okay. Thank you.
Thank
Yeah.
you. No, we didn't finish it.
Okay. Any other questions? Okay, maybe we could just have a look at the chat box. So we can
Ah.
open the chat.
Okay.
Okay, we have.
Yeah. Gege had the right comment. Yeah. So it's not quite important to show that quantum covariance vanish.
Right. Any other comments?
Yes.
Okay, we can open the chat box.
Yeah. I saw it. Yeah. Yeah. Adam Harper has very nice results.
Yeah.
So this epsilon can be removed, but we much more work, I think. Yeah.
I see. Okay. Okay. So let us thank the speaker once again.
Okay. Thank you very much.